Just a little introduction of myself and my company, Veracode. I'm the CTO and one of the co-founders. Veracode is a static binary analysis company, so we are able to do the kinds of things you can do with source code static analysis, but we do it on binary, compiled code, bytecode, things of that nature. You may have used some of the tools I wrote a long time ago, like LoftCrack and Netcat. And interestingly enough, Netcat has been flagged as a backdoor by some of the antivirus companies over the years. And I complain, and then they take it off their list, and then someone complains, and they put it back on their list. So just to go through what I'm going to talk about today, just some background on backdoors in general. And then talk about 4 classifications of backdoors that we came up with our research. And we did this by going through the history of the last 20 years of backdoors that have been discovered. So we know these can be found either, typically by inspection, static inspection. So we figured if it can be found by a person, there's probably a chance that we can automate that process. And that's really what I'm going to talk about today, is what are those rules to look for different types of backdoors. And then there's some additional detection techniques that you can do with static analysis on code just to see something suspicious is going on in the code. It isn't necessarily the backdoor mechanism itself, but someone's trying to hide something. They're obfuscating things, and that can be a telltale sign that you need to do further inspection. So if you can automate that process, you can run a lot of code through and zero in on suspicious areas, even if you don't know exactly what the code's doing. So to start it off for background, I thought I would play a little video clip here. And I don't know if most of you have probably seen the movie War Games, but this was really one of the first times that the concept of hacking and, interestingly enough, backdoors was introduced to the general public.
Jim. Oh, Lightman.
Hi, Lightman.
Why don't you take a look at this?
Hey, what's that?
I wanted Jim to see that.
Wow, where'd you get this?
I was trying to break into Protovision. I wanted to see the program for their new games.
Hey, wait, Jim, I'm not through yet.
Remember you told me to tell you when you were acting rudely and insensitively? Remember that? You're doing it right now. Theater-wide biotoxic and chemical warfare. This didn't come from Protovision.
You bet it didn't. Ask him where it did come from, Jim. Go ahead, ask him.
I told you already.
Looks military to me. Definitely military. Probably classified, too.
Yeah, but if it's military, why does it have games like checkers and backgammon?
Maybe because those are games that teach basic strategy.
Jim, how do I get into that system? I want to play those games.
You're not supposed to see any of that stuff. That system probably contains the new data encryption algorithm. You'll never get in there.
Hey, I don't believe that any system is totally secure. I bet you Jim could get in.
Yeah, I bet you couldn't.
I bet you he could.
Well, you'll never get in through the frontline security, but you might look for a back door.
I can't believe it, Jim. That girl's standing over there listening, and you're talking about our back doors?
Mr. Potato Head. Mr. Potato Head, back doors are not secrets.
Yeah, but Jim, you're giving away all our best tricks.
They're not tricks.
What's a back door?
Well, whenever I design a system, I always put in a simple password that only I know about. That way, whenever I want to get back in, I can bypass whatever security they've added on. That's basically what it is.
Yeah?
Okay, you really want to get in, find out as much as you can about the guy who designed the system.
Oh, come on. I don't even know the guy's name.
Where are you guys dumb? You guys are so dumb. I got this thing all figured out. I figured it out all by myself.
Oh, yeah, Melvin? How would you do it?
The first game on the list. Go right through Falcon's Maze.
So if you've seen the movie, you know that this is actually how Matthew Broderick's character ends up playing the games and breaking into this this system. So this is 1983. Probably every programmer knows about backdoors, knows they're capable of putting them in. Jim says, "Hey, I always put one in. It just makes it easier for me to debug things when things go wrong." But obviously, this is a huge security risk, and I don't think that the industry has a reasonable process for looking for this, except manual code reviews that are probably functional code reviews, not necessarily looking for backdoors. So just to break down into three major categories of backdoors that people often talk about. First one is a crypto backdoor. So this is the person who designed the crypto system has designed a weakness in the system that if they know about the weakness, it makes the work factor for them to decrypt messages a lot easier. So this is always what people worry about with secret algorithms. Who knows what it's really doing, and people are always suspicious that even published algorithms, if they're made by organizations like the NSA, they're smarter than us and they figure out how to put a backdoor in there that we can't look fine through analysis. But I'm not going to talk about that today, but just interesting to be aware that that's something that cryptographers look for. Now, system backdoors, what people typically talk about today when they talk about Trojan horses and rootkits. This is something where someone has installed software that's not supposed to be on the system that compromises the security of the entire system. It could be just changing the configuration of the system, like an RHOS file or something like that, to leave the system wide open. So I categorize those as system backdoors because you're attacking something really at the system level. What I'm going to talk about today is what I categorize as application backdoors. And application backdoors are a legitimate application that's supposed to be installed and running on the system, has some code within it that allows you to bypass the security of the application. So you can get at the application's transactions, the application's data. Now, it could also be a system backdoor if it gave you system access, but it doesn't necessarily have to. You could think of a shopping cart application that leaked the transaction information, the credit card, to an anonymous email address. That would be a backdoor of that application that's not supposed to be there, but it doesn't necessarily compromise the entire system. Now, application backdoors, like in the video clip, can be inserted by the people who have legitimate access to the source code or legitimate access to the binary distribution point. They can also be inserted by people who break into those systems and modify them. So it's difficult to tell with the backdoors I'm going to talk about today which scenario that is sometimes. But in any case, in both scenarios, it's a security risk to the people running the software. There was a talk given last fall at the DHS that Dr. Reifer from Reifer Consultants on a DHS-funded study looked at the types of software sites that government employees are downloading code from and running on their systems. And he had some custom tools he built and just used some standard antivirus packages and came up with, like we would expect, if you're downloading code from places of unknown origin, you're going to get a lot of bad stuff. He found that there looked like there was backdoor type behavior in 23 out of the 100 software packages. So I think that there is bad code out there and legitimate software packages, and I think that we're just not looking hard enough. So these are the typical targets we found when we did our research on where backdoors were discovered. Web applications, web servers, appliances, operating systems seem to be the major targets of choice for obvious software that's all connected on the network, and the person who knows about the backdoor can connect to the systems. I think that the major motivation of this is it's another way to attack many systems at once. If you can subvert an application and that application gets installed and you can find it, you don't have to go looking for a particular vulnerability. You know it's going to be there just by the presence of the application. It's also, you're getting by any kind of IDS or antivirus because you're putting it in a legitimate application that's supposed to be installed, and the application traffic typically is what the application would normally look like on the network. The DoD has recognized this. They came out with a report in the fall called Mission Impact of Foreign Influence on DoD Software, and they're just starting to get a handle on the fact that they've done a pretty good job of changing the culture, and they have infrastructure type security, and they're patching their systems, and they're trying to configure them and lock them down. And now one of the the weak points, the attackers always like to go for the path of least resistance, becomes the software itself. Where is it coming from? What are people putting in that code? And just a quote from the paper was, high-end attackers will not be content to exploit opportunistic vulnerabilities which might be fixed and therefore unavailable at a critical juncture. They may seek to implant vulnerability for later exploitation. And this chart here is a chart I actually got from DoD Software Tech News, Secure Software Engineering, where this was, the names have been changed, I guess, to protect all the companies. But this is a typical large-scale government project. If you thought of something that was being built for the FAA or the Defense Department, this is how the code gets assembled from many layers of suppliers. A lot of them are from foreign locations. A lot of them you don't know who's subcontracting to who and where the code is actually coming from. The fact that there's no way to really audit this efficiently is obviously a problem. And if you're getting different components delivered to you in binary format, how are you going to really look for backdoors in that? So as far as detection techniques, while it's possible to detect some backdoors, like ones that are probably doing unintended network activity, it's possible to detect them dynamically by looking at the system at runtime. But in general, you need to do static analysis or code review, because by their very nature, this is unintended functionality that's not exposed in the functional specification of the program. So how do you know what to look for? That makes this a difficult problem to solve. It's always going to be imperfect. The reason it's difficult is the behavior is intended to be hidden from someone looking for it. So that obviously makes it a problem. One thing I gathered from doing the research on the last 20 years or so of backdoors that have been discovered is backdoors that were planted in binaries typically were there for years. There were many versions of the code over a long lifetime of a software project that backdoor existed. There was one case where it wasn't detected, which I'll talk about, for 7 years. That was Borland's Interbase product. It was only detected once the code was open sourced. On the contrary, software that's open source software, backdoors seem to be detected pretty quickly. So the many eyes theory of open source is more secure definitely seems to be working, at least for backdoor vulnerabilities, where the vulnerabilities usually last in the order of a few days or a few weeks before they're discovered. So today I'm going to talk about using static detection methods. So the first major category, and probably the most common we found, is the special credential category. And it's interesting that backdoors show up a lot in popular culture and in the Matrix. The key maker basically knows he can make keys to all these backdoors that are in the Matrix because he knows where they are. So essentially, that's what a special credential backdoor is. It's a special username, password, or key that's embedded in the program, or sometimes it's computed off of some static value in the program or in the system. And that special credential allows you to, bypass the normal authentication in the system. So this is like Jim talks about in the War Games reference. He just puts an extra password in. So the first example of this was found in Borland's Interbase, and it was in versions 4, 5, and 6. It was discovered in 2001 after the code had been, a few months after the code had been open sourced. Someone was just trying to learn about how this program worked. He was looking at the authentication functionality and said, wait a second, something very odd is here. And what the person who put this backdoor in did was they inserted, whenever the database started, it went and checked and inserted a special credential into the password store. And if you knew this special password, it ended up being username politically and password correct, that you'd have administrative access to the system that this was running on. And so this lasted for over 7 years in the software. So here's the code that actually implements it. So you can see here that there's a couple of pound defines. The pound defines were actually in some other file. I've just put it here for convenience. So they kind of, you see that a lot of times, slight methods of obfuscation, just kind of separating the strings with variables. And then, so what we see here is it takes the locksmith password and calls the crypt function to create a password hash to then go and insert in the database down here. So right away we can see that, here's a recipe for looking for people trying to bake in, static passwords into the program. We can go and we can look at the crypt functions and see if any of the sources that are going into those crypt functions are coming from static values. And if they are, that's probably something suspicious that we want to inspect. Second example was found, this was found through binary analysis. A colleague of mine at Stake, Brian Hassick, we got one of these net structure SSL accelerators in, and we wanted to figure out how it worked, see if it had any vulnerabilities. Figured it, we're putting this SSL accelerator in front of, high transaction secure servers. So if it has a vulnerability, it's going to be pretty serious. So we looked at the code on there. We opened it up, found out it was running NetBSD, and started looking through the login code. And we found something very strange in the code, that there was a password that was being computed that it would check against when you entered your password. It would check against this static value, which was computed off the MAC address of the primary Ethernet controller. So this, to us, looked like something that the manufacturer put in specifically in order, if someone had locked themselves out of the appliance, that they would be able to say, oh, well, read me the MAC address on the back of your your appliance, and I'll give you the password, and you can get back in. And so we find this theme a lot, where appliance manufacturers will put a backdoor in that they think that only they're going to discover, right? But really, once the attackers discover, what they've done is they've put in this huge gaping hole in a device that's running in a security critical context here. It ended up resulting in root privileges on the appliance. And you might say, well, it's the MAC address, so it's not going to be, that serious a problem because someone on the internet can't see the MAC address, but someone on the local area network can look at the ARP table after scanning that network, and they can determine the MAC address that way. So it was a remote vulnerability. This next was another special credential backdoor in a shopping cart application. This was in a binary. This was a shopping cart you installed on IIS. And this was also found. Someone was doing manual binary analysis in a disassembler or a debugger, and they found that there was a hard-coded password that whenever someone logged in, it checked the password against a static string, WEMILO, probably someone's nickname, we checked for versions back, and we found that this was in 5 years. It was put in the code 5 years ago. It's hard to tell whether this was a backdoor that the manufacturer put in, the guy who wrote the program, whether it was put in there purposely or not. But obviously, it was a huge gaping hole that allowed you to find out things about the shopping cart and execute arbitrary commands on the system. And another appliance type situation was with APC's smart slot management card, which you could put in the server, and it had a telnet interface running on it that had a hard-coded password. So anyone could, take the EEPROM off of this device and look at the code and find this baked-in password, and then have access to systems over the telnet port. So just looking at those 4 examples, we can draw some conclusions on, what rules are we going to use to look for other backdoors of this type. So, being able to identify static strings, being able to identify, that they're not binary, that they are ASCII, because typically they could do binary, but typically people will do ASCII. They think they're not going to be found. And then look for known crypto API calls and seeing if a static value ever goes into one of those, and that's going to be a suspicious activity. And then if someone doesn't want to do that, if they want to actually put the static hash value in the code, you're going to look for static values that look like hashes. So they're going to have a known length to them. They're typically going to be if they're in a static string, they're going to be hexadecimal. And then finally, you can look for static values that look like crypto keys to see if those are compared against. And you can do that because ultimately they have to have a particular size, and they have to end up being sent to the crypto algorithm. Interestingly enough, this will find just any kind of baked-in static key, which by itself is a fairly common vulnerability that I found over the years for products that they want to get that checkbox that they use encrypted communications over the network. So what do? They just use symmetric encryption, and they just bake a key into the client and the server. I found one of these in a McAfee antivirus management product about 4 or 5 years ago. They were doing this. And a final thing you can do to try to figure out if someone is hiding keys in the software is to do statistical tests for randomness on the static values. You could do this, on the binary, or you could do it once it's been loaded into memory. You could do it at runtime. If you just scan through memory and do statistical analysis on chunks of memory that are the size that keys typically are, if you find something random, it's probably something that someone's using specifically because they need a random chunk of data, or it's probably a key, or it's probably something that's been obfuscated. So again, that's something that's sort of a telltale sign that something needs further investigation. The next category of that I found was hidden functionality backdoors. And here, this was actually mentioned in Battlestar Galactica, where one of the Cylon agents puts in some special functionality that can shut down I forget what it shut down actually, but she put in some special functionality into the software that she had access to, so that at the right time when they were attacking, they could trigger this functionality and it would shut down the navigation system or something like that. And so the idea behind this is you're not trying to bypass authentication. You're just putting in commands that if you authenticate normally to the system and you know about this command, you have special privileged functionality on the system, or sometimes you can put this command in to an area of the software which is unauthenticated. And now you have these very high privileges on the system without authenticating at all. One of the places we found this was this concept of invisible parameters in web applications. Not to be confused with hidden parameters. These are parameters that if you send them in a get or a post, some functionality happens, yet those commands are never exposed during the normal operation of the system. So we know that they really were not intended to be used, or they were intended as debugging functionality probably. And in general, just any kind of debugging functionality or undocumented commands that are left in the software when it ships to users, if those are discovered, at a later date, the person, an attacker, is essentially getting this powerful debug functionality that they can control the software with. We also found that sometimes people try to limit that with special IP addresses. So they'll put in special debugging functionality, and then they'll check the IP address that the connection's coming from, and that way, when the stuff's floating around outside the internet, the debugging functionality wouldn't work. But we also found cases where that failed. So one of the earliest examples of this in an internet application was, and I'm sure there was earlier ones, but IRC in 1994 was backdoored. The distribution was backdoored with these two commands, jupe and grok, which essentially just allowed you to execute commands on the IRC client of whoever you were talking to over the channel. So you could execute a command on their system. And this was found, since it was open source, it was found in a few months' time. But this was one of the earliest ones that was found and reported. Much more recent is a vulnerability in WordPress from last year. This looked like a case where it was malicious intent. It wasn't the developers that did it, because the download servers were compromised and the distribution was changed to a backdoored version. So this was detected in about a week. Someone discovered that this was in there, probably by sometimes people will detect that there was a compromise on the server. Sometimes someone will detect by inspecting of the code. But if you look at the code here, the way that they implemented the backdoor was they put in these two invisible parameters, IX and IZ. So if you know IX and IZ are invisible parameters that in effect are new commands on the system, you can embed those in a URL. And if you put IX in there, what it did was, if I can find my mouse, it called this comment text PHP filter, and with the value, it passed that to the eval function. And in PHP, essentially what that does is it will execute the contents that you pass to it as PHP code, so it'll just execute that code. And then if you pass the IZ parameter, it called get theme command, which called pass through, which is PHP's version of the system command. So it would just send that out to the operating system. So this ended up being a system backdoor also. And shortly thereafter, and it may have been the same person who did this. They played a little cat and mouse game. Essentially, they did almost the exact same way of inserting this hidden functionality into the software, but this time they used obfuscation. And what they did was they created this base64 encoded string, which had the PHP code they wanted to execute, and they encoded it. And at runtime, they did eval base64 decode that string. And if you run base64 decode on there, essentially you get something very similar. This one's not trying to be hidden at all. The commands are include, command, and PHP. Essentially, they allow you to execute PHP or any command on the system. So you can see that this whole backdoor hunting is going to be somewhat of a cat and mouse game, because whenever you find a technique that people are using and you come up with a way of scanning for it, people will just be coming up with new techniques. But on the other hand, there's a lot of backdoors that are in the code for years and years and years. So if you're looking for, if you discover a new technique now, if someone's used it, planted the backdoor 5 years ago, you'll detect it. So even though it'll be a, essentially a cat and mouse game in current time, because you can look back through old code, finding new techniques and running them retrospectively is a valid model for finding these things. The Quake server in 1998 had a backdoor which looked like it was a developer introduced feature. If you knew there was a archon command. This actually is maybe more of a special credential backdoor. And you knew a hard-coded password TMS, you were able to execute any command on the system. In this case, what they did was they checked to see if the command came from subnet 192.246.40, which actually turned out to be a subnet owned by id Software. And what they did was they thought, oh, this is a way of, we could ship with this debugging code in there, and we've protected it from being a backdoor. The problem was this command executed over UDP. So it allowed you to spoof the source network, and everyone could come from that subnet, essentially. And I think they fixed that one rather quickly. TCP wrappers was another example of some hidden code that was functionality. Essentially, it put in a shell so that whoever was running TCP wrappers would also have a shell running on their system on port 421. This one was found within 12 hours. So I think when it's really security critical software like TCP wrappers and it's small and easily auditable in open source, these things are going to be discovered pretty quickly. I put this one in kind of because it's humorous. This is one in courtesy of the daily WTF, and what they did was they used an invisible parameter, and the invisible parameter was called backdoor, and they checked to make sure if you set that to secret. So not much obfuscation what was happening here. So at the very least, grep your code for the word backdoor. So just to summarize some of the detection techniques for this one, a common pattern of obfuscating things in scripting languages is to use any kind of built-in encoding functions. So look for those built-in encoding functions and see if those ever get, if they're ever called and then the values are ever sent to eval, because that's a clear sign that someone's trying to obfuscate the code. Another thing you can do, which actually I was talking about some of this with a three-letter agency here, and when I mentioned this one, it really raised some eyebrows, and I think some of them ran to start looking at code. Is to identify commands in the software that come through get and post commands that are acted upon, but never appear in the HTML or JSP or any pages that are rendered to the user. Because then you can clearly do a diff between what the program is capable of processing and what the inputs of the program are supposed to be. And you can quickly see if there are any commands that were left in the code, debug commands or something of that nature that aren't supposed to be there. Another technique is just looking for OS command injection. This is something that you should be doing anyway, doing any kind of a security audit or any static analysis tool should be doing this. But if it ends up, a lot of these hidden functionality, people just want to call system command with the input that they're sending in. So if you have detection for OS command injection vectors, you're going to find a lot of backdoors that way. And just if you're doing a human audit, this is not as easy to automate, but if you're doing a human audit, really look for those command loops and audit every single command that's processed by those command loops and make sure they're all supposed to be there. Another technique which kind of crosses over through many different types of backdoors is if someone's doing something on a specific IP address that's baked into the software statically, that's a telltale sign that something fishy is going on and it should be audited. So unintended network activity is a third category that we found several instances of. And there was in the movie Police Academy, there was an instance of this where this guy created a popular computer game that he knew he would get installed onto very secure networks, which he normally wouldn't have any kind of access to. And I think what the backdoor did was it leaked sensitive information outbound so that he was able to get information from very secure networks. And that's sort of the threat model that the government is really worried about. So the characteristics of this is it's listening on an undocumented port. That's probably something that you can find fairly easily. Makes outbound connections. Could be easy if it's an outbound connection that the program is supposed to be doing. I mean, could be hard if it was something the program was supposed to be doing. Like maybe the program does send mail. Well, if it's sending sensitive information over mail, that's going to make it more difficult. We also found that in certain cases, the activity, this network activity, was hidden from the administrator on the local system because there was rootkit behavior in the software that tried to hide the network activity from someone who was inspecting the system at the host level. So you could inspect it at the network level from another system is a much better way to find these. So in 2002, someone modified the OpenSSH distribution, and they put in a test case called BF test, and it was masquerading as a test case for Blowfish for this specific platform, HPUX. But when you compiled and built OpenSSH, what it did was, instead of this test case just running and saying, okay, all the math is right on this system, I got my big endian, little endian right, I got my size of my words right, and that's what these test cases are typically for. Instead of doing that, what it did was it created a shell script out of what looked like data and ran it on the system. And then what the shell script did is it created a command and control channel on the IRC port, which allowed you to have remote shell access. So anyone who built OpenSSH got this system backdoor installed. So the delivery method for this was a legitimate application, but it ended up creating a whole separate process and running a separate process on the system. So it's really kind of a hybrid between an application backdoor and a system backdoor. And here's the actual code that did that. You can see up here, this is the data that's going to end up in the shell script that looks like it could be test case data. But if you look down here in this for loop, you see that it's taking that data and it's XORing it with 47. So this is the obfuscation technique. It's printing that out. It's printing those XORed characters out into a file. It prints them to standard error, but standard error is redirected to a script file, and then that script is executed. A few months later, a very similar vulnerability showed up in libpcap and tcpdump, which looked pretty much the same, except it did it on port 1963. But the interesting thing about this one was they modified tcpdump so that if you did tcpdump and were looking for what's going on port 1963, it would be hidden from the administrator. So this is sort of the inklings of rootkit-like behavior where your backdoor is modifying the program to hide its behavior from the system administrator. And this is just a snippet of the code that actually strips out monitoring port 1963. I always wonder where some of these things come from, like is this the guy's year of birth or something? There's got to be some telltale signs in the way that people write these things. Edomite is a content management system for the web, and it's written in PHP. And instead of being a hidden command, this was unintended network activity. And so, let's see here. So they used the obfuscation technique of base64 encoding it, and then when you decoded that, it ended up sending some data, server name, and the I'm not sure what this value is, if it's the version number of the server, out to this email address, cijfer@neti.fi. So again, this is just an unintended behavior of the program. Probably an anonymous remailer, if I had to guess. So to detect these kinds of vulnerabilities, backdoors, we're going to look for the network socket functions, and we're just going to audit all the socket functions in the program, connect, send to the Win32 equivalents. Going to look for any hard-coded IP addresses and ports, and make sure those are ports that the program is supposed to be communicating on. And then this was a little more tricky and probably needs to be done manually, but analyze what kind of data is going out over those connections. If it is a legitimate, say it is legitimately sending some information to another server, is that information sensitive? Is it stuff that's supposed to be going out over the network? And a way to specifically look for sensitive information is look at the stuff that's going in and out of the crypto API functions. That's a pretty good sign that it's sensitive data. One thing you can do very trivially is just looking at the import table of the software. This is something that you can just really quickly do. If the software is not supposed to have network activity, but it's linking to the network APIs, probably want to dig in more. So that's just a quick check to see if there's going to be any unintended network activity for a program that's not supposed to be doing it. The last category we came up with was manipulation of security critical parameters. And there was a few cases of this that were discovered. So the idea behind this is put in some logic in the program that in certain cases security critical parameters are changed. So an example of that might be the UID, which is managed by the kernel, the UID of the process. If you could change what the UID was, put a backdoor in that changed that, that would give you some powerful access on the system. But it could be other things. It could be privilege bits. It could be, protection on memory changes. It could even be scheduling priority. If you could have a backdoor that could manipulate these, that might be something that's pretty hard to audit for. On the application side, applications have some critical variables like in authentication authorization functions, what role someone is in. If you could manipulate those, you get extra access on the system. So the first case we could find of this was in the Linux kernel in 2003. And someone attempted they directly modified the kernel CVS tree. So they had some vulnerability in the system that was housing the CVS tree for the kernel, and they directly manipulated the file, and they made this change. It's only 3 lines of code. Can anyone find the backdoor change in there? That's right. So where there's it should be a double equal there in the second line, where it should be checking to see if the UID is equivalent to 0. Instead, it's the assignment operator. So if you called the syswait function on a system with this backdoor with the wclone and the wall variables, you would execute that 1 line of code and set your UID to 0. So this is a very, very subtle change that might be very difficult to find with manual review. It actually turns out to be really trivial to find with static analysis, to see that there's an assignment going on inside of a conditional, which is something that could potentially be suspicious. This was actually not detected by auditing the code, though. It was detected because the way that they inserted the backdoor, changed the files in the file system, corrupted the transactions in the log, and because they directly manipulated the file, and the CVS got corrupted, and so they said, hey, something is going on. We got to figure out how this happened, and they looked at it and they found that this one file was changed in this one way. So the guy who came up with this idea blew it at the last minute, I guess. Now, a very similar thing happened more recently in the XOR server, and I believe that this was found by Coverity using their static analysis tool. They detected this one. Can anyone look in this code? It's actually in a couple places where the backdoor is. So this one's along the same lines as the other one. It's really subtle. If you look here, the comparison is to get UID. It's checking to see if that's equivalent to 0. And then it does here is it checks to see if get UID, but instead of calling the function, it's just checking whether the function pointer is not equal to 0, which is pretty much always going to be true. So by removing the parentheses, they've changed the behavior of the program. And then that was in 2 places. And looking at this, it's probably a mistake. It could have been, the other one could have been a mistake too, but we know it wasn't because the machine was, the CVS machine was tampered with. But this one could have just been a legitimate mistake. It was in 2 places though, so it's hard to tell. In any case, it's a vulnerability that should be looked for. So to find these, in summary, to find these, you really want to identify what security critical parameters are in your program. So if it's something like, the Linux kernel, you could enumerate those things, and there's not going to change for many, many years, and you could audit all that every time you came out with a new release, make sure no one's tampering with those values. You could do that with, and look for assignments instead of compares, or look for the missing parentheses would be another case. Another case that we found was people just will short circuit an expression, and they'll just put a value that always evaluates into true. So in a function that is normally checking something security critical, like is authenticated, they short circuit that with something that's always true, and it'll always authenticate at that point. So now I just want to talk about some additional techniques that don't fall into any particular category, that are signs that someone is doing one of these things, whether they're trying to bypass authentication, whether they're trying to send out sensitive information to the network, they're trying to do hidden commands. These other techniques find those sort of root kinds of backdoors. So one of them is embedded shell commands. If you find embedded shell commands in the code, it's probably something is up. Looking at timing information, or looking for obfuscation techniques, either hiding at runtime with rootkit behavior, or hiding statically with obfuscated code. So these are things that you can just do with grep. You can grep for things like binsh. These really silly things are so easy to do. You might as well do them. Look for functions that are typically used to obfuscate, encoding and decoding, XOR, ROT13 type functionality, and then looking for time functions. There's a lot of reasons why programs legitimately need to get the time. Whether they're trying to round robin something, they're trying to send it to write out the log, write out the time to a log file, a timestamp, an error message. But typically it's a very small set of things that are done with the time, and it's easy to audit that and make sure there's no time bomb in the program. Rootkit-like behavior is a big telltale sign that something is up with a piece of software. If people are hooking the Windows API and trying to change what that API is returning back to a caller from another program on the system, that's pretty suspicious activity unless it's a system tool. If your music player, for instance, happens to be trying to hide its behavior on the system, which happened with Sony's music player last year, that's pretty suspicious activity, that something's going on that you probably, as the user of that program, don't want happening. And there's whole books on how to write rootkits. So I'm not going to go into that here, but if you look to what people are doing to try to detect rootkits on a running system, you can translate that to how to detect it statically by people calling the same kind of functions that rootkits call at runtime. And then finally, any kind of self-modifying code is probably suspicious. You may want to do that. Maybe you're trying to protect some secrets in your program. I think it's kind of a futile attempt to try to do that because someone will eventually reverse engineer it. But sometimes people try to do that for legitimate reasons. Other times, self-modifying code is a big telltale sign that the program is trying to hide something from the people doing a code audit. This was a case I talked to some banks about the backdoors that they found, and of course I can't show those as examples, but on code that they had written for them. And one of them gave this interesting example of they found that the people who put in the backdoor knew about their code auditing process, and they knew that they only audited the piece of code that changed. So from one release to another, they did not re-audit the whole program again, they just audited the changes. And so if you know that that's someone's process, you could insert a backdoor in 2 stages. You could put half the backdoor in on one release and the other half in the other release, and then when they talk to each other, then it creates the backdoor. Otherwise, it looks like innocuous code. So that's why unreachable code should be suspicious, because it might lead to something at a later date. And it's also probably a bad idea to just do partial partial code reviews anyway, because most vulnerabilities come from, long data flows through the code. They're not always just within one basic block of code. And then sort of humorously, we found that even programs that were malware had backdoors in them. We found an example of Optics Pro, which was I think it was a remote access Trojan that someone published in binary form only. Happened to have a 38-character master password embedded in it. So whoever downloaded this malware and used it to compromise systems was also compromising those systems for the creator of Optics Pro. So I guess, don't trust your malicious code not to have backdoors in it either. And this also happened in Sub 7, which was an earlier Trojan program. The final category, which I'm going to talk about, is just exploitable vulnerabilities. What if the person who's putting in the backdoor is really good at writing exploit code? So they could put in a buffer overflow or a SQL injection or some other vulnerability in the program that gave them ability to run commands on the system. And then if it ever got discovered, no one would think anything was up. Everyone would think, oh, he just made a mistake when he was coding up the application. So it gives that plausible deniability. If you're worried about someone tracing back to you and saying, oh, well, this person is the one who checked in this code, or had this small set of people had access to this code, if that's the scenario, you could just put in an exploitable vulnerability and hope that there's no other mitigation at the system level that is keeping it from happening. So this really blurs the difference between a vulnerability and a backdoor. So it's just some final thoughts. When backdoors have been found, it's typically been worse than when a vulnerability is found when it gets discovered out in the wilds, because they're trivial to exploit. They're just designed to be a text command or a special password. You don't need any special tools, techniques, or anything. So pretty much everyone can exploit a backdoor once it gets out. And interestingly enough, because I'm always looking into how companies are reacting to news that their products are insecure, and I found that when a backdoor is discovered, or people are claiming that a vulnerability is really a backdoor that someone put in, it's looked at as a more serious problem with that company's software, because it really looks like they don't have control of their whole software development process. Because not only are they writing insecure code, but I can't even trust their development team. They're using code, or they have people there that are intentionally putting bad things in their software, and then I'm going to use it. So it ends up being a much worse PR problem for companies if there's backdoors discovered in their software. So when do you want to scan for these? I would say you need to scan your code. I come from a static analysis company, and I definitely think that everyone should be using static techniques to scan their code before they ship it. But you also have to wonder, if you think back to that slide I had in the beginning, which it had the long supply chain of software where someone writes a library and then sells it to someone else, and they bundle it into their software, and then that gets bundled into a bigger software package. You actually don't know where a lot of that binary code came from. So when you're out there buying packaged binary code, or you're using open source libraries, you can't trust that code either. So you need to look at sort of an acceptance testing process if you're a developer of the code that you're linking into. Finally, I think that sort of the grandfather of backdoors and thinking on backdoors is Ken Thompson. And I highly recommend this paper that he wrote, Reflections on Trusting Trust. And if anyone doesn't know Ken Thompson, he was one of the creators of Unix, and he wrote the original login program. And what Ken Thompson did was he put a backdoor in the login program so that he had his own special password that he could use to get into any Unix system. So obviously this is a huge gaping hole. But he also delivered it as source code. So he knew that his colleagues were going to discover this. So what he did was he backdoored the compiler so that whenever the compiler detected it was compiling the login.c program, what it did was it would put in the backdoor code. So the code got inserted at compile time. And then what he did was he said, well, what if someone looks at the compiler? So he went one level beyond that, and he actually compiled the compiler with the backdoor code, and then only distributed the compiler in binary form. So you had a compiler that was backdoored to write the backdoored code in login, and everything was available in binary form only. So you could look at the login.c program, audit it, fine, but when you compiled your system, you got your backdoor. So he went one step even beyond this, and he backdoored the disassembler so that if you disassembled the binary code to look for backdoors in the login program, the disassembler would hide the backdoor code from you. So this guy kind of did it all, right? He covered all his bases. So an interesting thing is, can we trust our development tool chain? Can we trust our compilers and linkers that they're not inserting backdoors into our code? Can we trust our disassemblers that they're not hiding the backdoors that are in the code from us? So, I'm paid to be a professional, paranoid guy because I'm a security guy, but it's hard to know whether that's actually going on. So with that, any questions? Yep.
Had any concerned companies about the liability, aside from just PR impact and being financially liable? Most people sign 10-year license agreements, but with this kind of stuff going on, it seems like you would have a higher concern if there was backdoors.
Sure. So I actually haven't, I totally agree with you. I mean, if I was a bank outsourcing some custom code to be developed and it came back to me with backdoors, I'd probably be pretty concerned about that. And in those custom coding environments, we are starting to see those things be written into the contracts where there is some liability there. But it's usually when it's a large financial company and small development house. When you get to packaged software, I don't think there's anything besides your standard end user user agreement going on. Anything else? Oh.
I've also heard of some phishing toolkit software which fits up a backdoor and sends like credit card numbers to the person who wrote the toolkit as opposed to the person who's deploying the phishing software.
So that doesn't surprise me at all, seeing like the Optics Pro had a backdoor in it, and obviously code that's being delivered from sort of someone who's writing malicious code to other attackers is going to be highly suspect because who can trust who? No honor among thieves kind of thing. Okay, well, thank you.